for Doctors Without Borders. You guys rock, even if you didn't donate. Because you're going to, after this, aren't you? Yes, yes, yes. Right now, awesome. The wireless does work, mostly. All right, enough joking for now. Welcome, everybody. I hope you are awake after lunch, because this is internal level session, level 400 in the Query Optimizer. I don't know why they put it after lunch. I would have thought they'd put someone like Brent Ozar after lunch. You can, no. I don't dance, sorry. Was he dancing? Go back Grant. He'll be on after me. You thought Grant and I were the same people. No, I assure you that's a complete myth. We have been seen together. Who started that silly rumor anyway? All right, statistics, heuristics, and row estimations. I'm going to be talking about the cardinality estimator, a part of the Query Optimizer. This is intended as a level 400. I will probably drop up and down the levels a little bit. But to be honest, if you don't know what a query is, this is probably the wrong room. I say that because last year I did a 400 level session on indexes, and I had somebody ask right at the beginning, what's a where clause? It didn't get much better from there. Can I cover the where clause before I start? Didn't ITSIC do a best session on basic T-SQL? All right. Does this work in SQL 2000? Most of it actually works back till 6.5, believe it or not, except for the part that says SQL Server 2014. I'm not actually joking. No, SQL 7. 6.5 is a little too archaic. Does anyone still work with SQL 6.5? My condolences. It's not there anymore, I promise. You guys have a SQL 6.5 server? Somebody at the back? Somebody said yes. I hate to break it to you, but that thing's like 30 years old. All right, you've seen this slide enough times. No. Yes, please, session evaluations. We do like them. More to the point, we like them usable. Not been nasty, but a session rating which says you suck is useless, because you didn't tell me why. If I suck, please do me the courtesy of telling me why I suck, so that next year I can suck less. No, seriously, I had a rating last year that just gave me ones across the board and didn't say a thing. I'm sort of, okay, somebody didn't like the session. I don't know why. Take session rating, discard. I can't use it. If you're going to give a speaker feedback, give them useful feedback. Doesn't have to be nice, doesn't have to be nasty, but should be constructive. And mind the insults, please. I know some people like them, but in general, if a session rating says you're an idiot, I just discard it because, yeah. All right, that's done. So the agenda. I have roughly an hour and, well, I have until Grant throws me off the stage, which should be fun enough by itself. We are going to talk a little bit about what the cardinality estimator is, what it does, why it's important, because this thing's actually critical. Just a quick show of hands. Who knew that something called the cardinality estimator existed before today? Awesome, wonderful. Who knew that the query optimizer existed? Actually, I should ask who didn't know that. We're going to look at row estimations. I'm going to spend the majority of the session looking at the row estimations that the cardinality estimator comes up with. The idea here being that once you know how it generates these estimations, you have something you can do when it generates them incorrectly. Because unfortunately, the cardinality estimator is rather prone to making mistakes. It's not because it's stupid, it's because it's got an incredibly complicated job. So if you've got incorrect row estimations, the first thing you need to do to figure out why is to understand how it came up with them. Once you know how it came up with them, you can possibly address why they're wrong. The majority of this will be on the filter predicates. That's your equalities, your inequalities. Because further up the tree, it's kind of hard to work with them. The estimations are set at the leaf level of the query plan. Further up, there's not all that much you can do. By the way, I hope you're at least familiar with a query plan. Grant's going to go into detail on them after me, but as long as you know what a query operator is, we should be good. I'm going to talk about the changes in 2014 towards the end. Now, this is probably going to give me some negative reviews on the topic of, you didn't talk about the new stuff, but there's a reason for that. Who has 2014 in production? SQL Server 2014 in production. Great, what's that, 10%? Yeah. 2012? 2008? Or R2? 2005? You'd know it's out of support. Actually, you know 2008's out of support. So is R2. 2000? My condolences. Would you like a sledgehammer? 7? No SQL 7 boxes. Okay, we've covered the 6.5s. SQL 6? 4.3? 4.2? I've seen somebody with SQL 6 in a presentation before. How many years ago was that? Probably about 2. All right, almost everything I show you here, no, let me rephrase that. Everything I show you in the first part of this presentation is valid from SQL 7 up to 2012. The 2014 changes I will touch on at the end. I'll cover those. I'll explain what's changed. But the vast majority of this is applicable to the vast majority of your servers. I would love to come here one year and have everybody running the latest version. It ain't gonna happen though. Right. Row estimations, why do we care? We care because they're essential for good query plans. Grant will probably spend 15 minutes saying the same thing. That was not an insult. Good query plans require good row estimations because the operators in a query plan are not all appropriate to all row counts. Some operators in a query plan work well on a small number of rows. Some work well on a large number of rows. There are a few that don't care. But even the ones that don't care need to know how many rows, approximately more or less within a reasonable error, will be coming through for purposes of things like memory grants, deciding what order tables should be joined in, where the aggregates should be done. All of that kind of thing requires that the optimizer knows the row counts, which is a problem, because it needs to know the row counts before it runs the query. It can't just go and run the query to get the row counts, because this could be a query that runs 3 hours. So it's got to quickly come up with an estimation of the row counts for a query before running the query. And this is the job of the cardinality estimator. It is incredibly complicated. It's not quite as complicated as the rest of the query optimizer, but it's not far off. Oh yes, and the row estimations affect whether you're likely to get parallel plans or not. If the estimations are low, you'll probably just get serial plans. If the estimations are high, the optimizer may well consider parallel plans. Not necessarily saying it will give you parallel plans, but it may well consider them. So all of this shows why we need good, accurate row estimations. They don't have to be dead accurate, but they are not going to be very useful if they're off by 3 orders of magnitude. My general rough rule of thumb, 1 order of magnitude is where you start really worrying in most cases. Beyond that, it's a disaster. Less than that, you can probably get away with, in most circumstances, with a large number of exceptions. Right, so how are they generated? Yeah, complicated. There's a whole pile of things that the cardinality estimator will do. It uses the statistics, if they exist. That's your index statistics and your column statistics. It uses the parameter value if it knows the parameter value. I will get into why it might know it later in a further slide. It'll use unique constraints. It will use primary keys. It will use foreign keys. And this is why foreign keys are good for performance in databases, because they give the cardinality estimator additional information. The data types, to some degree, not massively, but I have seen cases where the data type can affect what the row estimation is. And the one thing to note, this has changed quite a lot in 2014. 2014 contained the first major set of changes to the cardinality estimator since SQL 7. I think Microsoft was just scared of touching it. Yes, sir? When it comes to constraints, does it have to be a unique constraint or is a unique index acceptable? A unique something. A unique constraint is just enforced with a unique index, so it's a unique index under the scenes. Unique constraint, primary key constraint, unique index. All of those three are, as far as the cardinality estimate is concerned, fairly equivalent. Right. So, row estimations at the bottom of the plan. This is your table scan, index seek level. This is where the rows actually come from. This is where I'm going to spend the majority of the rest of this presentation. Because if the row estimations are wrong here, there's not a bloody chance in hell they'll be correct at any other point. If they're correct here, they might go wrong further up the plan. But if they're wrong here, they're going to be wrong. So we'll look at a whole bunch of scenarios, and I'm going to walk you through exactly how the estimations are generated in a lot of cases. These are the cases. We're going to look at equality with statistics, with and without known values. So that's when the optimizer can sniff the value and when it can't. Going to look at equality when there are no statistics. Everyone here, does anybody here have auto-create statistics turned off on their database? You do. Do you go and create statistics as necessary manually? You don't. Okay. Auto update is off. Okay, that's different. Does anyone have auto create turned off? No, okay. I ran into somebody a few years ago who turned auto create statistics off on all of their databases and ran a manual job every day to delete any statistics that might somehow have been created. I'm quite sure his query performance was spectacular. That would work if every single query in his database returned one and only one row. That would actually be fine. My gut feel is that's not the case. Anyone got a system that every query only returns one row? Yeah, I don't think so. I haven't seen one of those either. I'd love to see one. That would be funny. Yeah, please don't go messing with those auto-create, auto-updates unless you've got a good reason and you're willing to do the work that they would have done themselves. Right, so equality without stats. The main case where that happens is table variables, because table variables cannot have statistics on them. Anyone ever converted a query over to use a table variable and suddenly surprised why query performance goes through the floor? No one? Probably lack of statistics. Horrible, horrible effects. I'm going to look at inequalities, because they behave quite differently, with and without known values. And you notice I don't say without stats, because there's some interesting things about inequalities. I'm going to look at multiple predicates, and I'll look at that when I touch on the 2014 differences, because that's where they mostly come into effect. And I'll talk about a few special cases. I'm not going to show them in most of them, because they're kind of hard to generate, some of them. But we'll talk about them so that you know they're there. Right. First, some definitions, because if I keep talking about these and you don't know what I'm talking about, there's going to be lots of confusion. All right, these terms are often misused. I apologize if I'm insulting anybody, but they are. So a predicate. A predicate is a logical expression which returns true, false, or unknown. It's unknown because we are in a database world and we do have nulls. So this is any of column equals 5, column greater than 17, column is not null. All of those kind of things are predicates. Where clause predicates, join clause predicates. I'm mostly going to be talking about where clause predicates. Columns have density. The density of a column is defined as 1 divided by the number of unique values in that column. It is a measure of how unique that column is. Columns have density. Indexes can have density because they're based on columns. Predicates have selectivity, and selectivity is a percentage, and it is what percentage of that table the predicate matches. You can have a very high selectivity, which is not a good thing, by the way. It's a measure of 0 to 100. A very high selectivity, 100%, on a column which is absolutely unique. Think about where column greater than 0 on an int identity. It's going to match the whole table. The column's unique. The predicate is not selective. Finally, cardinality. Query operators have cardinality. It's the number of rows they affect. It's an actual physical number. It is not necessarily a whole number in the case of estimations, but it is a number. Is everyone happy with these? Because I'm going to be using these without further explanations. Everyone happy? Okay, good. Equality with statistics and with a known value. The known value can come from a stored procedure, because when a stored procedure runs, the first time it runs, it is compiled, and the optimizer knows at compile time what value the stored procedure was called with, what value the parameters had when the stored procedure was called. This is called parameter sniffing. It is a good thing, usually. It can be a constant, because if it's a constant, the optimizer knows exactly what the value is because it's constant. And it can be a variable if and only if the query has the recompile hint on it. That's not with recompile on the procedure. That's the option recompile query hint on the query. Because if a query has that hint on it, the query is sent back to the optimizer right before it executes. And at that point, the value of the variables is known, and hence the optimizer can sniff them. That makes sense to everyone? This is critical. All right. So when the value can be sniffed, the optimizer knows exactly what the value is that it is looking for at compile time. At the point it's compiling the plan, it knows what to look for. When it knows what to look for, it will take the statistics on this column. It will take the known value that it has. It will go to the histogram of the statistics. I will show this in a demo in a sec. It will find that value. It will find where that value falls within the histogram, and it will read off the values it will read off the row counts that value has within the table. Let me show you this, because this is a little more complicated than can be done in explanation. So I have a bunch of statistics here. This is what statistics look like. 3 sections. We've got the statistics header, which just has the name of the index. In this case, it's an index. This was just a statistics object. This would be some other name. When they were last updated, how many rows are in that table? 5 million rows in this table. How many steps in the histogram? Ignore this, it's wrong. It's completely meaningless. It had a meaning back in 2000 days, it's a leftover. Average key length, on average, how many bytes does this index's key have? There's no average here, it's an 8-byte, it's 2 integers, 2 4-byte integers. Is it a string? Is it a filtered index or filtered statistics object? If it is, the filter goes here, and this shows you how many rows were actually in the table, and this shows you how many rows that the statistic affects, or statistic covers. This is obviously not a filtered index. The header. The density vectors. For each left-based subset of columns, and this is an index, so we can have multiple of them, we get the density of that set of columns. So this column has this as a density. That, remember, 1 divided by the number of unique values in that column. So I could invert that to find out how many unique values this column has. Actually, I'll do that because I feel like it. If I can find my inversion. So there are roughly on average 3,000, looks like there's 3,147 unique values in this column in 5 million rows. The trip ID is the clustered index. So being the clustered index key, it's present in the non-clustered index. So the combination of this column and the clustered index key has that as a density. The clustered index key in this case is the primary key. It is unique. So that is actually 1 divided by 5 million. Not so interested in this one. This one's going to be interesting later. And the really interesting part, well, this is the histogram. There are up to 200 steps in a histogram. Now, it cannot possibly contain all the unique values in the table. There are over 3,000 of them in this table. So what SQL does is it figures out some interesting values for the high keys. And how it does this is unfortunately very undocumented and not very well known. This is the magic of the cardinality estimator, or the query optimizer, should I say. What is known is that when the statistics are created, it will try to ensure that these high keys are interesting values. So if you've got a really weird data distribution in your table, on average, most values are there 100 times, but 1 is there 100,000 times, there's a good bet that that 1 that's there 100,000 times will be a high key, because it's interesting, it's different to the rest of the table. This value, it's the high key of this range. So this row tells me how many, this row contains the information for the values between 2,808 and 2,823, exclusive. Sorry. Right, range rows. This is how many rows are between these two values, exclusive. How many rows? This is how many rows equal this value. This is how many distinct values are in this range. So there are 9 distinct values and 16,800 rows. And then this is the average. This is on average how many rows, sorry. This is on average how many rows each of these 9 values has. So does that make sense? Is everyone happy with that? Sorry about this. All right, so if we go and look for this particular station, and I'm using option recompile because I don't want cached plans to interfere with my queries. I'm not saying this is a good thing to do in general. I'm using it in a demo situation. 1,302. And it looks like I've had a query update. Wonderful. One problem with playing with statistics, if you rebuild indexes, your statistics histogram goes completely differently, and all your demos promptly break. Right. All right, this one should work a little bit better. Estimated number of rows, 342. And you will note that the actual row count is identical. Probably because I haven't changed this table since I updated the statistics last. So if we go and look in the histogram for this station, 1710, it's a high key. Equality rows, 342. That's where my estimation came from in this case. In this particular case, the value that the optimizer knew it was looking for happened to be one of the high keys in the histogram. And so it could simply go and read off the value for how many rows equal this high key. This is obviously not the normal case. I've got a lot more values than I have in this histogram, but this is the easiest case. Right, next one. This is not a high key. My estimated row count in this case, 1375.29. Just as a general point, you can often tell whether you've hit a high key value or not by looking and seeing whether the estimated row count is a whole number or not. If it's a whole number, you've probably hit a high key value. If it's got a decimal places in it, it's equals doing it as an estimation on a range. So that was 1375.29. Right, 1998. Let's go find this in the histogram. 1998 is somewhere between these two values. That was 1998. Right. Thank you. At least someone's paying attention. I'm obviously not. All right, so this is the high key, so this is the row I read off. I don't care, and I'm not interested in that one. This is what I'm looking for. This is, on average, how many rows equal any value within that interval, and on average, it's 1375.286, rounded to 29. Make sense? Everyone following so far? Any questions at this point? Is everyone still awake? Okay, good. Just checking. It is after lunch. Yes, sir. If you write in the middle, is there a preference? So that's the high key. It's the two values are the beginning and end of the range, and the range you're looking for is always on the high value. So it's not, yeah. The value with the upper end of the interval contains the information for the interval. Sorry, the question was, if the value we're looking for is in the middle of the range, is there a preference for beginning the row at the beginning or the row at the end? But the point here is that the histogram value is the high key. So you're always looking at the row after the range, not the row before the range is irrelevant for this range. So does that make sense? Yeah. I hate Microsoft. You thought all they gave was computer viruses. Well, I spent 3 days before PASS Summit at MVP Summit, and a couple of us came down sick. You'd think they don't want us back there. All right, so that is with known values. In this case, the optimizer knew exactly what it was looking for. Let's try when it doesn't. I have a variable here, and I'm not recompiling this. So when this runs, the optimizer gets a query that says, I want to find a row with a particular station. No, I'm not telling you which one. That's a surprise for later. So the optimizer cannot use the histogram in this case, because the histogram requires that I know what value I'm looking for. Right, so no rows. That's interesting. Estimated rows, 1,588.81. Actual rows, 0. Blame the data generator. 1588.81. Where this one comes from, because we cannot use the histogram, because this only helps us when we know what we're looking for, we fall back on the density vector. This, remember, is the average density of the column. I can take this, multiply it by the number of rows in the table, and I can use that to work out, on average, how many rows match a particular value, even when I don't know what that value is. But this is an average density. So if I take this, and I multiply it by the number of rows in the table, 1588.81. 0.81. That is my estimation when I have a value that I don't know what I'm looking for. I have a variable, I have a parameter where I've used option optimize for unknown. So let me just switch back to the slides because okay, equality with stats with an, okay, so let me, all right, so I've just done the demo for this. Let me talk my way through this. Equality with stats without a known value, the optimizer does not know what value it's looking for. So this is a variable, or if it's a parameter, I've specified the option optimize for unknown hint. Tell the optimizer I don't want it to know what the value is. In this case, it uses the average density in the column to work out approximately more or less on average how many rows this value will match. This works fine if your data is evenly distributed. If your data has peaks and troughs, this will not work too well. The question was, what about dynamic SQL? Depends on what the dynamic SQL sees. If the dynamic SQL sees it as a constant or a parameter, the optimizer knows its value. If it sees it as a variable, it doesn't know its value. The rules don't change when you've got dynamic SQL. It's just another batch. All right, so does this make sense to everyone? Any other questions? Sorry? So no, when there's a parameter in a stored procedure, will it optimize for unknown? No, optimize for unknown is a query hint. You put it on a query if you don't want the parameter to be sniffed. If you declare a variable, you get exactly the same behavior. It's just a little bit easier to just shove option optimize for unknown than to go and declare all the variables. It's less typing. That's about all it is, though. Does that answer? Okay. Oh, no. He's a friend. Don't worry. I can pick on him. My general rule, if you're a friend and you're sitting in the front row, I pick on you. If you're not a friend, then I don't. No, I can't pick on strangers. They tend to take it badly. Feel free. Awesome. Thank you. All right, so this is equality with statistics. I've covered the two options. Is everyone happy with at this point? All right. Equality without statistics. Sheer bloody guess, because there's nothing else we can do. At this point, we've got no clue what the distribution of the data in the table looks like, because there's no statistics. SQL always knows how many rows the table has. The storage engine knows that. So it always absolutely knows accurately how many rows are in this table. But without statistics, they could be unique. They could all be the same value. They could all be null. We've got no clue whatsoever. So as soon as we've got working without statistics, the optimizer is taking a sheer bloody guess. And one of the easiest ways to get no statistics is to use a table variable, because they don't have statistics. Right, so I'm going to declare, go away. Thank you, Microsoft. The virus update is out of date. Yes, well, it's a Windows 8 machine with a toolbar that doesn't want to go away. I love Windows 8. All right, so I've got a table variable. I'm going to put 50,000 rows into it. If you remember, this table has 5 million, so 1% of it, 50,000, simply because I don't want this to take too long. And then we're going to go and see what estimation we get when we query the table variable. Does anyone here think I'm going to get a row estimation of 1? No? Ah, some people do. I'll talk about that in a sec. All right, we've got no rows. And we'll ignore the insert into. All right, this is the query. Estimated number of rows, 223.607. Okay, where the hell did that come from? I hope that was what I was expecting. Not what I was expecting. That's worrying. All right, let's try this again. Hope this works. No, apparently it doesn't. All right, something's gone foobar here. It usually does. Let's try that again. All right, the reason is that the table variables always estimate one row is a myth. Unfortunately, it's a very common one. It's a myth with a whole bunch of good reasons behind it. And it comes down to the unit of compilation. Table variables have a scope of the batch, which means they are created, populated, used, and or automatically dropped within a single batch. The unit of compilation is a batch. So at the point that the batch is compiled, there are no rows in the table variable because it hasn't been compiled yet. It hasn't been executed yet. It hasn't had the inserts run into it yet. So at the point of compilation, the optimizer looks at this and says, how many rows are in this table? Oh, it doesn't exist. 1, because it doesn't exist. Table variables don't have statistics, therefore they don't trigger recompiles like temp tables do. And therefore, when the query runs to query that table variable, it doesn't get hit with a recompile, and it gets the same plan it got at the time the whole batch was compiled, which has a row count estimation of 1 for the table variable. Because it was empty, it didn't exist when the batch was compiled. Does that make sense? Everyone happy with that? I was getting a row estimation other than 1 because I had a recompile hint on my query. So the query got sent back to the optimizer after the table variable had been populated. And at that point, the optimizer went and said, oh, a table. How many rows are in this table? There are 50,000 of them. The storage engine knew that. Does that make sense to everyone? That's where that one row myth comes from. You will see one row in most cases because most people don't drop recompile hints on queries using table variables. Since one of the advantages of a table variable is that it doesn't cause recompiles. It kind of doesn't make sense to forcefully recompile something that as a feature doesn't cause recompiles. So yeah, that's where that one row story comes from. Does everyone follow why these were not one row? Everyone happy with that? My row estimation is still not what I expected it to be though, so we'll probably call this a demo failure. It happens. Yep, estimated rows is definitely not what it should have been. I am running in compat mode for 2014. Thank you, you're right, I am. Always reset your demos before doing presentations. This is something that's changed in 2014. Thank you for catching that. Who was that? Thank you. I'd have been sitting staring at this for the rest of the afternoon. All right, let's try this again and it'll actually work. You got a taste of the 2014 changes early. I can try. All right, still no rows, but that I expected. Estimated row count now is exactly what I expected to be, 3343.7, 3,343.7. Now the fun question is, where's that come from? Because we've got no statistics. We've still got no statistics. The recompile didn't generate statistics. All we've got at this point is the total number of rows in this table, which is what the storage engine knows. We've made a complete guess. And the way we've done this is the total number of rows in the table raised to the power of 0.75. Without statistics, SQL's got no option for estimating the rows, so it falls back on its heuristics, and it uses that simple formula to get a rough estimation of how many rows this query might affect. Where that came from? Hell, I've got no idea. It took a while to even figure out what it was. I remember 3-4 years ago, there was a long thread on a mailing list trying to figure out what this equation actually was. I think somebody graphed it in Excel and did a formula fit. So yes, those statistics, complete, absolute guess. And by the way, just so that I prove that one row estimation that I'm talking about, if I take this out and run this again, I love table variables, so blazingly fast. There's what probably most of you were expecting, estimated rows, 1. No recompile, table was empty when the batch was compiled. Everyone happy with this? Any questions at this point? Happy to take them. Right, so that's pretty much that for equalities, mostly. I'll come back to equalities in a bit, but I want to get the other predicate type done. Inequalities. These are a lot harder to estimate because I can't use the density map to estimate inequalities. It's useless. The density map, the density vector, tells me on average how many rows of a value are in the table. It's not very useful when I'm doing range searches. So inequality. With statistics, with a known value, this one works fine. Again, we go back to the histogram. This works very much like equalities did. We go up to the histogram, we look up the value, and at this time, we use the range rows instead of the average range rows, and basically sum them up over the intervals that the query covers. This is not actually that hard. Inequalities, same statistics. Fun thing is I've got no internet access, so I don't know what it expects to do anyway. We have an estimated row count, 38,713. And you'll note that the actual row count is dead on identical, so a very, very accurate estimation here. It's accurate because, again, we just happen to have hit the high key values for the table, for the histogram set. Let's have a look at this. Same histogram as before. 1695. Somewhere around here. 1695 through 1720. So what SQL's done here, this range rows is irrelevant because this is the upper value of this boundary. So we don't care about this. So we've taken these two values, 16,222, 19,288, and added them together. 35,500, not quite. Plus, this was an inclusive search, so plus the equality rows for this value, plus this, plus this. One important point here, the range rows in your histogram are exclusive. They don't include the number of rows which match the high keys. They're an exclusive range. So when you're trying to do an inequality check for the estimated rows, you need to add up the relevant range rows and then add up the equalities, the EQ rows of any range, any high key that is within that range. Make sense? Yep. That's with a known value. Okay, let me show you this one. This is just a single-ended inequality, and this is not a high key. And we've got 17,643.8. Okay, 4,000. So 4,000 falls somewhere between these two. What SQL is going to do is it's going to try and extrapolate how far along the range that value is. So if the value is halfway between the two high keys, it'll take half of this. If it's 3/4 of the way through, it'll take so it'll take a quarter of this, because I'm looking for the range above. So that's why you end up with a decimal place, because we've taken this value, the range rows, we've divided it, we've taken a fraction of it to try and figure out where in that range we are, and then added the rest of the ranges up to the end of the table. Is everyone following? Does this make sense? Yes, sir?
Why wouldn't it be using the range row value from the higher value instead of the lower value?
Sorry?
Earlier when you were showing, you clicked on the 3994 and said it would use a fraction of the range rows.
Sorry.
Okay.
No.
Just want to make sure I understood that right. Thank you.
I'm confusing myself here. No, it won't be using this one, because this is the values between these two. It'll use this, sorry. It will use a fraction of this, and if there were more ranges, it would add them together. Sorry, the previous demo I had 3 high keys up. Apologies for that. So yes, this being the high key, it's part of that range. How much through the range, depending on the ratio, the point within that range, within this gap that the value we're looking for falls. I think I've confused everyone now, myself included. Does that make sense? Right, slides. Equality with stats without a known value. This is interesting, because I didn't have to say with stats, because the stats are completely useless here. I don't know what value I'm looking for. I can't use the histogram. I have an inequality. I can't use the density. So the statistics are actually completely useless in this case. I've got an inequality, and I don't know what I'm looking for. Here's a table of 5 million rows. I'm looking for rows where the value is between something and something else. Well, your answer could be anything from 0 rows to the entire table. The optimizer has no good way of estimating this. Like with the equality without statistics, it falls back on its heuristics. We've got statistics, but they're useless. And the formula is actually very, very simple. If it's a range search that only has one end of it, so that's a greater than or a less than, where some column greater than 5, the estimation is 30% of the table. If it's a range that's got 2 ends, so this is either a between or I've got a greater than and a less than, then the estimation is 9% of the table. Those are fixed, because there's nothing else it can do here. Inequalities are very, very hard to estimate the row counts for. Does it make sense? Yes, sir. Yes, ma'am. If there's 2 betweens, hold that thought. There's an old joke from a few conferences ago. I believe it was Itzik who started it. A good question is one I can't answer. A great question is on the next slide. That's a great question, because it's on a future slide. Hold that thought. I'll get to it. All right. Inequality without stats. Well, we weren't using them anyway. Same, in this case, it falls back on the old 30%. This is very much the same as its previous estimation. I think that slide's actually incorrect. I think it's exactly the same as the previous one, the 30% and the 9%. The stats were useless when it didn't know the value, so no stats, okay, it'll behave like it doesn't know the value. Same kind of thing. Everyone happy with that? Because that is inequalities. Any questions on these? Right. Multiple predicates. See, I said it was on the almost next slide. Multiple predicates are interesting. Prior to 2014, the optimizer assumed that the multiple predicates were completely independent. So it assumed that if predicate 1 affects half of the table, and predicate 2 affects 10% of the table, then the combination of the two affects 5% of the table. Because nobody ever designs tables that have columns which are correlated, right? Oh, lovely. The problem with that is we do design tables that have correlations between the columns, and that's one of the examples. The combination of city and state, city and province. I assure you, we only have one Johannesburg in South Africa. It's in Gauteng. I don't think they've built another one in Cape Town yet. So the combination of the two doesn't reduce the rows at all. I could have just filtered for where city equals Johannesburg and got, hopefully, exactly the same rows back. If I don't, there's some data quality issues. That's somebody else's talk. So this was a problem because it generally results in the row counts going ridiculously low. I will demo this when I get to the 2014 portion. Just one comment on this right now. When you're doing database design or you're writing queries and you're using 2012 or below, consider whether you need all of your predicates. If you're writing a query like this, province and city, make sure you actually need both of them and you're not simply adding predicates for no good reason, not reducing the row count, but giving the optimizer a harder time. Because this can actually seriously, seriously hamper a query. Yes, Hugo, what are you about to do to me? If there's an index on province, you'd absolutely keep them in. If there was an index on province and not on city, I would absolutely put an index on city and throw the province query away. Look, there's... Don't mind Hugo. Apparently, I'm about to get some viciously nasty feedback from the front here. That's okay. I'm coming to your presentation later, Hugo. All right, so does this make sense to everyone? I know this isn't something you can always do. It doesn't make sense to do it in all cases. But if you are writing queries, just have a look at your predicates and make sure that you're actually reducing the rows correctly and not just adding extra predicates in for no good reason and messing up the estimations. So does everyone understand this point? And if you're designing tables, same kind of thing. Think about whether this belongs in a table. Or does it belong in multiple tables? Do I need to split my tables apart? Do I need to store the province if I'm storing the city? Do I need to store them in the same table? That kind of thing. Will system-generated statistics help with that? Not in the slightest. Because system-generated statistics are always single-column statistics. A multi-column index might help. It might, or might not. But system-generated statistics are not going to help in the slightest, because again, it's simply going to take the row estimations from the first, the row estimations from the second, and multiply them together. Multiply the selectivities together. So no, it doesn't help, unfortunately. Anyone else? All right, some special cases. Unique constraints, unique indexes. The optimizer doesn't have to work too hard to figure out that an equality match on a unique column returns one row. There's one reason why if a column is unique, it should get a unique index or constraint. Pick your option. The fact that if you know it's unique, tell SQL that it's unique. It gives the optimizer more information. It potentially also allows the optimizer to do fun things like discard aggregations if it knows that it's never going to have to aggregate. I saw a lovely one the other week, a query that grouped by the primary key column. Thank you, that was smart. Let me just take the group by out and strip all of these sums out. It didn't improve the performance in this case, because SQL knew full well it didn't have to aggregate. But it may be cases where you've got unique columns which are not marked as unique, where SQL's doing additional work that it doesn't have to. So unique constraints, unique indexes, really, really useful things. Put them on if you know your columns are unique. And please don't listen to your developers when they tell you that they will enforce uniqueness in the application. Anyone got a developer like that? Okay. This is getting filmed and my devs are watching, so I'm probably going to get slammed when I get back to work for that one. All right, when the predicate can't match any rows, the non-nullable column is null. That one doesn't work very well. No, you're not going to get any rows returned from that, assuming, of course, we're not doing strange things like joins at this point. I'm talking literally about a predicate that cannot possibly return any values. So if you're asking for where the column that cannot be null is null, the optimizer knows that's a big fat 0 rows. And in fact, it's got some very interesting simplification abilities. Contradictory predicates. If you've got two predicates which cannot possibly both be matched, a row cannot at the same time have a column value greater than 10 and 0. Again, no need for estimations at this point. That's 0 rows. It's going to be thrown out. The bottom one's interesting. Top exists and row count. Now, I believe Adam does a full hour-and-a-half presentation on row goals, so I'm not going to do this justice in 5 minutes. I will simply say that it is possible, in some cases, in some query forms, if you have a top, for that value in that top to be pushed down into the query plan and be the estimation. For example, select top 10 stuff from table, you end up with an estimated row count of 10, completely regardless of how many rows are actually there. The statistics don't get touched. The top is used for the estimation. This does not happen in all cases. I spent a good few hours earlier this week trying to generate a case where it happened, and I couldn't. But I've had 6 of them at work in the last couple of months. So if you see a query that's got a top, and your row estimation is off, and you're not sure why, check the value in the top and check the value in the row estimation. If they're the same, you've hit this. The row goal that the top has put in has been pushed down into the estimations. How you fix this is amusing. I've seriously not found a good way of doing it. I've taken to occasionally nesting tops within a query. I've sometimes inserted rows without the top and then deleted the excess. That was a fun query. So you will see this occasionally. It doesn't happen often. Yes, sir. Top with a variable, here you're probably going to hit parameter sniffing. If that's a parameter, the optimizer knows what it is at compile time, so it can use it. If it's a variable, it hasn't got a clue. I don't honestly know what it'll do in that case. But 100 rows. Okay, that's, Okay. The gentleman in the front says that if it can't figure out the value for a variable top, the estimation is 100 rows. That's lovely. You guys, does this get fixed in 2014 as well? You don't know. I haven't even been able to generate one of these in a demo. It's one of these scenarios which tends to resist reproduction in simplified environments. But I'm mentioning just so that you know it's there. I've seen this in a few cases, and it's damn annoying when it shows up. At least if you know what's happening, you've got a better chance of fixing it than if you don't know why you're getting a top 10 on a row, on an operator that's returning 10 million rows. All right, let me just demo these special cases quickly. They're not all that interesting. All right. No, I didn't do that. Not sure what that's supposed to be. All right, so this one, I've got a non-nullable column. And what you'll notice is I don't even have a query plan. Optimizer was smart enough to figure out that that cannot happen. There is no way a query that looks for a null value in a column which is defined as not null can possibly ever return a row, and so it doesn't even go and look at the table. I don't even think this one got as far as a cardinality estimator. There's a part of the, it's part of the algebraizer, I think, contradiction detection. Let's pick this one up. Same thing here. That's not at all possible. And so again, same thing. Estimated rows, 1. It's a constant scan because it's returning the metadata. That's all it's doing. So those are the fun, interesting scenarios that you will occasionally see. All right, joins, moving further up the tree. I spent the majority of the time on the bottom of the query plan. Get the row estimations right there. They might be right further up the tree. Get them wrong there, not a chance in hell. But interesting points further up the tree. For joins, what SQL will do is it will take the histogram of the two join columns, and it will do a linear interpolation of those two histograms to try and figure out, more or less, how many rows this join will return. It is capable of being spectacularly wrong. Fortunately, it's not usually spectacularly wrong. It's usually reasonably okay. But if you've got weird histograms, if you've got strange data distributions, you might see cases where your join estimations are miles out. And no, Microsoft doesn't make very much information on this available, unfortunately. Aggregations, that one, it uses the density vector. The density vector will tell it how many unique values a combination of columns has, assuming, of course, that it has an index on all of the group by columns. If it does, it can use that to tell how many unique values that combination of columns has, which will tell it how many rows the group by returns. This, of course, assumes that you have some decent indexes. If there aren't indexes on those combination of columns, again, we've got guesswork. I think it also simply multiplies the predicates, the selectivity predicates together, giving you some kind of interesting results. And distinct is behind the covers, behind the scenes, under the covers, that's a group by. It's treated the same way. Let me show you the joins very quickly. All right, joins are around here somewhere. All right, so what I've done here is I've created 4 tables. This has rows 1 to 100 in it. This has rows 1 to 100. This has 50 to 150. And this has 300 to 400. So this is a perfect one-to-one match. Returns 100 rows. And my join has an estimated rows of 100. Perfectly correct. Perfect interpolation of the histograms. It's very likely in this case that my histograms are very, very accurate because I've only got 100 values. Larger tables, you wouldn't quite see this kind of accuracy. This one's only going to return 50 rows, 51. My estimation here has come in at 20-ish. 21.9. So the interpolation's not as accurate. It's not going to be perfectly accurate when you're comparing 2 histograms which have got different high key values because it's trying to figure out how these 2 histograms match together. And the complete non-overlap of the 2, no rows returned. And because the histograms are completely distinct, the optimizer is smart enough to figure out that there's no way in hell these two are going to join. Of course, this assumes that your statistics are accurate. Everything I've said here today assumes that your statistics are accurate. I created mine after populating the database. If your statistics are off, all bets are off. Right. Any questions on the current behavior up until 2012? That's what I've been talking about all presentations so far. The 2012, 2008, 2008 R2, 2005, 2007 behavior. Any questions at all on that? SQL 2014, everything changed. Almost everything. It's interesting, this feature wasn't given much marketing rah-rah. It's probably one of the better features in 2014 because a lot of the problems the cardinality estimator had have been fixed, or at least partially fixed. In general, it does a much better job. In general, you will probably see query performance improvements going to 2014, in general. They've also managed to smooth out and remove strange edge cases where things suddenly go wrong. I do say in general because it is entirely possible to get performance regressions moving to 2014 because of the new cardinality estimator. If you're moving a 2012 database up to 2014, please test the performance of your queries before and after, because you could be up for some really nasty surprises if you get one of the edge cases where there is a query performance regression. The first important thing, multiple predicates are not assumed to be independent any longer. It's actually assumed that you might actually have some form of correlation between columns in your table. So we no longer have such a major problem of the estimated row counts dropping when you have multiple predicates. It's still not perfect. I'm not even sure it can ever be perfect, but it's a hell of a lot better. All right, when the parameter value is out of the histogram range, this was known as the ascending key problem. Anyone hit the ascending key problem? Oh yes, you're going to love 2014, people, because it doesn't exist there any longer. The assumption in 2014 is if the parameter value we're looking for is beyond the bounds of the histogram, that it's actually there. Go figure, that we're actually looking for rows that really exist. And because the histogram doesn't cover that range, SQL will fall back on the average density. So in 2012 and before, if SQL was using a known value to look up the row estimations, so it was using the histogram, and the value was beyond the boundaries of the histogram. So for example, my histogram ended at 4,100 some odd. If I was looking for 6,000, 2012 and before, I would get an estimated row count of 1. In 2014, the assumption is that beyond the bounds of the histogram, we will fall back on the density vector to find out approximately how many rows on average we're likely to have. This is going to fix a lot of sudden unexpected performance problems. That's probably one of the better parts of it. Joins. They don't do linear interpolations of the histogram any longer. They just consider the min and max values. That's not necessarily a good or a bad. It's just different. You will see some queries that give better estimates from that. You will see queries that give worse. It's a change. In general, your estimation is going to be more consistent. You're not going to have the cases where suddenly those estimations just go horribly wrong. You can't figure out why. It's in general a lot more consistent and a lot smoother. All right, so how do you get this? Well, first you install 2014, because no, they don't backport this kind of stuff. We could dream. Database must be in compatibility mode 120. If you don't want the new cardinality estimator, it's as simple as keeping your database in compat mode 110. You saw the effect the compat mode had earlier when my demos broke. I'd accidentally switched into 2014 mode. Just change the database compatibility mode. We'll turn the new cardinality estimator on or off. If you don't want to play with the compatibility mode, there are two trace flags. 2312 to get the new one, 9481 to keep the old one. You can use those as query trace on hints if you want. I believe that still needs sysadmin permissions though. Or you can just turn it on as a global trace flag. Take your pick. All right, one more demo before Grant throws me off the stage. Is Grant here yet? Oh, good. Right. Grant. No, I still have 8 minutes. Okay, sit down. All right, changed in 2014. I'm not quite sure why I put that one there. Ah, yes. So I've got perfect correlation between these two columns. Absolutely perfect. Yeah, I designed the table stupidly. Yeah. So if we look at the row estimations for these two, they are going to return identical numbers of rows. 2,328 rows each. The row estimations for the first one is 1,889.41. That's not too bad. 1,800, 2,300, that's close enough for a decent estimation. Let's look at the second one. Now this returned exactly the same number of rows. 1.06. Estimated rows 1.06. That's what you get from adding a second predicate. It's taken the two selectivities, it's multiplied them together, and it's figured you're only going to get one row out of this. No, I'm not. That's 2012 behavior. All right, let's up the compatibility mode. Exactly the same query. All I've done is switch it to 2014. 1,889, same thing. 44 estimation here is 44.8. It's still low, but it's better than 1. Wouldn't you agree? I'm probably still going to get problems from that, but I'll take better if I can get it. So that's one of the first ones. Right. I'm not sure what the point of that was for. I was going to show some of the other ones, but they weren't quite working, and I didn't want to inflict more broken demos on people. All right, so that is, in a nutshell, the cardinality estimator, 2012 and before, and the changes in 2014. Some light reading for you guys. The definitions that I put on an early slide came straight from Bart Duncan's website. He was annoyed about how people misuse them, so he went to clarify what they actually mean, and people have been ignoring him ever since. If you want to know more about the cardinality estimator, Joe Sachs' blog on SQL Skills contains more than you could ever want to know about it. He went into a huge amount of detail on the backoffs, on the extended events, on all the new behaviors of the 2014 cardinality estimator in a huge amount of detail. He's written 20 or 30 blog posts there. And if that's not enough, he went and wrote the white paper, which is the fourth one down there. There's also 2 articles from PSS, Product Support, detailing what can go wrong, the major changes. And if anyone's got a Pluralsight subscription, the guys that were giving out 30-day passes in the expo hall, so take advantage of it. There's some courses on Pluralsight from Joe on the cardinality estimator. Right, any questions? We've got a couple minutes. Yes, sir.
So I realize this is mostly demo, but you use option recompile in a lot of your queries, and I know with 2012 and 2014, there's some problems with option recompile, where refresh my memory for you. Remember what exactly? There's a KV article out there that they had to.
Okay, let me clarify. Option recompile was there for demo purposes. This does not mean you should go and put it on all your queries. Please. I had somebody ask this at the user group. They said, you've put this here. Should we go and use it everywhere? No. I put it here because I didn't want query compilation issues. I didn't want cached plans interfering with things. Please, no. It's like all query hints. It's use it where it makes sense and nowhere else. Now, I use this for demo purposes, not, I should put it in 14-point font, 44-point font maybe. Yeah, no, it's not for all usage. Yes, sir. Will it behave differently with clustered column stores? You're asking the wrong person. I don't even know what a column store index is. Probably. Sorry. Find a BI person. You know what a column store is? You know what it is? Is that the limit? Cardinality estimator on column stores. Yes. Everything's going to be different. The density, the question is about the density map. It is the densities that are on the first column of the index, always, always. You do not get histograms of secondary columns. Okay, people are running away. Thank you very much. I'll be up here until Grant throws me off.